In this video, we're going to go over the real number system and talk about the differences between rational versus irrational numbers. Real numbers are made up of rational and irrational numbers. And there is a such thing as imaginary numbers. So you have real numbers and imaginary numbers. But imaginary numbers is something that you'll go over in Algebra 2. So for right now, we're just going to stick really to rational and irrational numbers. Now, rational numbers have smaller subsets, and the smallest subset is going to be natural numbers. Natural numbers is going to be your set of positive integers or whole numbers, and it's how we naturally count. So if I wanted to count these sheep, I would count it as 1, 2, 3, and so on. When I naturally count, I don't usually start with a 0. So I normally start with 1 and I go from there. So 1, 2, 3, 4, 5, and so on. So I'm going to go back here to my little Venn diagram here. And my smallest subset is natural numbers. And it's just starting like this. And it goes on forever. So 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. Now, whole numbers is going to be the set of positive integers, but it's going to include that 0. So as if we started with 0, then 1, then 2, 3, 4, 5, 6, and so on. And you'll notice that natural numbers are also whole numbers. So all of the natural numbers that you'll see here is also within our whole numbers. So all natural numbers are whole numbers, but not all whole numbers are natural because 0 is not a natural number. Integers is going to be the set of positive numbers and their opposites. And so I like to think of it as being what we normally see on a typical number line. And what it means by the whole numbers and their opposites is the opposite of a positive 1 would be a negative 1. The opposite of 2 is negative 2, 3, negative 3, 4, negative 4, and so on. So here we have 0, and there is no opposite of 0. 0 is just 0. So starting with 0 going this way, we have our positive integers, and then 0 going to the left is going to be our negative integers. So when I'm looking here, I'm just going to draw a little number line. This is what you normally see in like a classroom that they have up on the wall, that kind of thing. So our typical number line, no decimals, no fractions yet. So it's just our whole numbers and their opposites. As for rational numbers, that's where we start getting into fractions and decimals. So rational numbers is any number that can be written as a fraction where the numerator and the denominator are integers and the denominator is not 0. And we'll get to that not 0 part soon. So there's basically 3 ways to write rational numbers or to recognize rational numbers. And the first way is by fractions, like I just described. Then you have terminating decimals and repeating decimals. Terminating decimals are decimals whose digits end. Okay, so the digits stop or terminate, and that's where they get the name terminating decimals. Then we have repeating decimals, where we have decimals whose digits repeat. A pattern. Okay, And that pattern part is super important. So let's get into rational numbers versus irrational numbers and what they look like. So when it comes to rational numbers, they're predictable. So when you think about a person being rational, they make sense. They're predictable. And so with irrational numbers, they're going to be unpredictable. We don't know what they're going to do next. So with rational numbers, we have fractions. And remember, the top and the bottom, the numerator and the denominator, they both have to be integers, but they cannot have 0 on the bottom. So if I have something like 1/2, if I were to write that as a decimal, I know that that would simply just be 0.5. If I were to have a fraction like 2/3, I know that that would be 0.6666666 on forever, or I could put the little bar over it. So you'll notice that all of these fractions, when they have a integer on the top and the bottom, as long as the bottom isn't 0, it's going to be a terminating decimal or a repeating decimal. So when it comes to our terminating decimals, I know the number that's going to come next. So let's say I have 2.7. If I have 2.7 and I wanted to make it look more like money, I know that it could be written as $2.70, right? So when it comes to our terminating decimals, we know that I can put an infinite number of zeros behind it and it would go on forever. So that 2.7 is the same as 2.7000000 on forever. And that little ellipses, those 3 dots, tell me that this goes on forever. So terminating decimals are actually repeating decimals. We just don't see those repeating invisible zeros. Now, when it comes to repeating decimals, they can be written one of 2 ways. So we have 1/3, which is the same as 0.333333 on forever. So when I look at this here, I can tell that these 3's are repeating. I can guess that the next number is going to be a 3, and these dots tell me that these 3's are going to go on forever. Or I can write it as 0.3, and this line over the top tells me that this 3 is going to go on forever. So repeating decimals, as long as you see that pattern here with the 3 dots, or you have this line above that tells you exactly what the pattern is going to be, they can be written either way. But also keep in mind that we could have more than one decimal that repeats. So let's take 4 out of 99. So 4 over 99 is equal to 0.0404 on forever. And I could write that as 0.04 with a line over it. And that line tells me that the 0.4 is going to repeat on forever. But then you get some fractions that get really crazy. So let's say 9 over 35. It gives us a wild looking decimal. But remember, all of our fractions can be written as terminating or repeating decimals. So 9 over 35 is actually 0.25 5, 7, 1, 4, 2, 8. And all of these actually repeat. So we have 0.2571428, and then it starts again with the 5, 5, 7, 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, and it goes on like that forever. And we'll see this more as we do conversions between fractions to decimals when we're doing long division. So you'll actually see this later. So we kind of see what our rational numbers look like, but what do irrational numbers look like? So we know that the numbers actually don't stop, but we can guess that they cannot be repeating or have a pattern. So I could have just random numbers here. I could have something like 4 or 7, 1, 4, 6, 8, 9, and then my ... I have no idea what number would come after that 9. There's no pattern. There's nothing that tells me that this would start over again. There's nothing that tells me what my next number would be. So this is completely unpredictable. And these ellipses tell me that this number keeps going on forever. Then we have numbers like pi. And pi, sometimes we use 22 over 7, or we use 3.14 as its rounded version, but we know that pi actually goes on forever. Now, there are these mathematicians who have gotten up to 1,000 digits, and we have these supercomputers that just sit for a long time and calculate the numbers for pi. But all of them are completely random and we don't know what they are. So we have 3.1415926 and it keeps on going. Then we have these radicals or square roots. So if I take the square root of something like 2, well, there's nothing that multiplies by itself to give me 2, and that will actually give me an irrational number. So the square root of 2 is actually 1.4142135, and it goes on forever. So if there's a radical that I cannot simplify in using a perfect square, I know that that's going to give me an irrational number. So now let's go ahead and go back to our Venn diagram. So rational numbers can be those fractions. And just remember, I could have 1/3, but it could also be negative. So I could have a negative 1/3. I could have 3 over 4. Then I could have these decimals as long as they end. So I could have something like 3.56, and I know that my zeros would go on the end forever. Then I have things like 0.6 with the line over it, or I could have something like 0.04 with the line over it. So as long as I have that line, it tells me that it goes on forever, or I could actually write it out. And as long as I have established that pattern, I could say, hey, I know that a 0 and a 4 is going to come next. And with our irrational numbers, as long as you see the number pi, you're always going to know that's going to be irrational. So even if you see something like 2 pi or 2 over 3 pi or pi plus 3, it's always going to be irrational. And if you look at pi plus 3, okay, even if I have pi, which is 3.14159 and so on, even if I add 3 to that, it's not going to change the fact that it's still going to be irrational. Okay, and it's still going to go on forever. So anytime you see that pi, just automatically know that it's going to be irrational. So even if you see pi in a fraction, even if I take pi and divide it by 2, it's still going to give me all those crazy digits at the end. And then I have those radicals of my non-perfect squares. So if I have, let's say, 35, there's nothing times itself that gives me 35. And so I know that this is going to be an irrational number. And then we have our decimals that we just can't control. We just don't know what they're going to be. And they're always going to have this dot, dot, dot. If they don't have the dot, 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 that's just the same as a long terminating decimal. So just make sure you're really careful about that. It has to have this dot, dot, dot here, that it goes on forever, but there's no pattern here. So with this, I have 0, 4, 0, 4, dot, dot, dot. I can guess that the pattern is going to continue. Now with this one, there is no pattern, so I can't automatically say that this is going to be a 1826 again. So this is an example of an irrational number. Now, as I was talking before about radicals, if I have, let's say, the square root of 16, the square root of 16 actually simplifies down to 4. Because 4 times 4 gives me 16. So you definitely want to make sure that you're simplifying these radicals before you classify that number. Even if I have, let's say, a negative square root of 36, this is going to give me negative 6. And negative 6 is a number that I would see on a typical number line. So you definitely need to make sure that you simplify any radicals or even fractions before you classify. So I could also have something like negative 4 over 2. Although I would think like, oh, this is a fraction, it must be up here, I could actually fit this down into the integers category because negative 4 over 2 is just the same as negative 2. And negative 2 is also an integer. So definitely make sure that you're simplifying before you go further. And that pretty much sums up our real number system and our rational and irrational numbers. Now, the reason that I said that you cannot have a 0 on the bottom, so if I have a number here with a 0 on the bottom, you could also remember this as a number over 0 spells no, right? That's going to be undefined. The reason that is we like to think about fractions as parts of a whole, right? So if I have, let's say, a 4 over 0, I can't take 4 slices out of 0 pizzas. So this is going to be an undefined number. And so we're not going to call that a rational number just because it looks like a fraction. So you definitely want to be careful in realizing that your rational numbers, when they're written as fractions, they have to be integers on the top and on the bottom. Now, they can get crazy with, decimals and things like that. As long as they end up being terminating decimals or repeating decimals. And even with irrational numbers, I could have something like pi over 2. So not all fractions are going to be rational. They do have some rules, okay? And so anytime you see that pi, just remember that's going to be irrational. So that basically sums that up. And you also know what undefined means. And you've also heard about imaginary numbers, but we're not going to get there quite yet. Not for this lesson.